You're in a room with a red button, push it, and there's a 50% chance a machine ends your existence instantly. We run the experiment again and again. Statistically, you should be gone pretty fast, except in the worlds where you are. This is a thought experiment, not a guide. We'll explain what the latest science actually lets us test and what it absolutely doesn't. We'll move from this imagined scenario to what 2025 quantum technology can really measure, and then to why most scientists still see quantum immortality as speculation. So how close could that button get to being real? When probability becomes personal. Now imagine that the same red button isn't tied to a cartoon version of danger, but to a functioning quantum apparatus in a controlled lab. Not a paper exercise and not a dice-rolling classroom stunt, but a piece of working equipment capable of producing a clear, measurable result from genuine particle-level behavior. The stakes here aren't sketched in metaphor, they're embedded in processes playing out at nature's smallest scales. Each press could be decided by an event so brief and fine-grained that, until very recently, no device could catch it in real time with meaningful detail. The line between theory and direct measurement is narrowing quickly. In 2024-25, the newest generation of quantum computing systems isn't just about stacking more qubits for computational bulk. It's about vastly improving the ability to isolate, steer, and measure them. Engineers have driven gate speeds higher and slashed error rates. Recent 2025 reports from NIST SQMS and leading industry roadmaps show coherence and fabrication gains that let researchers monitor quantum dynamics at far finer timescales than before. Improvements in superconducting qubit fabrication and the stability of fragile quantum states extend how long these systems can maintain coherence, offering a sharper view of how qubits evolve and interact before decoherence sets in. That shift matters. Where experiments once produced only statistical averages, blurred pictures built from millions of trials, researchers can now probe quantum systems with unprecedented time resolution and see how probabilities change as the process unfolds. It's not about watching a wave collapse as if it were a visible spectacle, but about tracing the dynamics and decay of quantum states with enough fidelity to compare directly against the fine-grained predictions of theory. It's like moving from hearing a headline about a coin toss to following the internal movement of the coin in extreme slow motion, minus the coin, and with particles doing the unpredictable work. In the imagined button test, this capability could be configured so that a single qubit's measured state determines the big picture outcome. Press the button and the system couples that microscopic decision to a trigger. What happens next in principle would hinge on a result quantum mechanics treats as inherently unpredictable, no deeper facts within reach to tip the odds one way or the other. These technologies make it plausible to link quantum decisions to macroscopic triggers for carefully controlled lab demonstrations, though ethical and practical limits keep this firmly in the realm of thought experiments. Physicists like Max Tegmark and Robert Squires use scenarios such as quantum suicide to discuss interpretational questions, not as something to build and perform in reality. Because today's machines can sustain and observe qubits with greater stability, scientists can better chart how subtle environmental shifts alter their predicted behavior. Those measurements reveal the signature of quantum randomness, statistical patterns arising not from hidden variables we haven't found yet, but from the nature of the system itself. For the first time, query-by-query tracking of a quantum state's evolution is accurate enough to follow a single instance of a microscopic event and chart how its probabilities shift before settling on an outcome. That doesn't give physical proof of alternate timelines, it simply gives clarity about the kind of randomness that such interpretations take as their foundation. From here, the idea of probability becomes less abstract. Life events aren't normally tied directly to the flicker of a subatomic system, but we all live on paths containing split points we only notice in hindsight. The glass that didn't break, the step you took a moment earlier than collision. In a quantum description, every one of those moments could correspond to a branching of possibilities. Modern experimental techniques don't show us branches opening. What they do is expose the bedrock randomness that, over time, accumulates into differences at scales we can see and feel. It's possible to imagine a chain of such quantum-dependent events, each with odds stacked against the same outcome repeating. Within an interpretation that allows all outcomes to happen in separate branches, there's always one thread that makes it through every trial, improbable in any conventional calculation but internally seamless to the observer traveling that thread. You press the button, a quantum event decides the result, and in that narrative you remain. Any version of you in branches where the other result occurred has no more access to your continuing experience than you have to theirs. The fact that existing hardware brings microscopic quantum decisions close enough to be tied to mechanical outputs we can directly verify is a change in kind, not just in degree. In a demonstration, you could watch a display switch between two outcomes, its timing and frequency matching numbers dictated by quantum mechanics for that particular setup. In those moments, you're not proving many worlds or securing personal immortality. You're watching the kind of decision point that, in theory, defines the boundaries of your timeline. None of this constitutes evidence that anyone could survive an endless series of such trials, nor that parallel histories exist. But it does bring the underlying physics that make the thought experiment conceptually possible within experimental reach. The randomness governing subatomic systems can now be tied, under controlled and ethical lab conditions, to macroscopic events in ways we can monitor without relying purely on statistical averaging. So the next time you think about being the fortunate one whose side of the probability curve always seems to win, remember that the mechanics behind that feeling are no longer just textbook abstractions. They are processes we can measure with unprecedented precision, shaping outcomes in the tangible world even when every setup is identical. And that opens a door to the deeper question of why, when conditions are fixed, nature still produces variety at all, a question that becomes unavoidable the moment you leave the world of imagined buttons for the smaller, stranger world of particles. Randomness is the rule, not the exception. In the world we normally deal with, patterns feel dependable. If you take a basketball and shoot from the same spot with the same motion over and over, the ball's path and result will hardly vary. Gravity, air resistance, spin, all of these forces behave in stable ways at the human scale. Control the conditions closely enough and you get almost perfect repeatability. That's classical cause and effect, reliable rules producing reliable outcomes. It's the basis for building bridges, flying planes, manufacturing electronics, and baking bread the same way twice. Now take that same mindset and shrink it far below what the eye can see. Replace the basketball with a single particle, say an electron fired toward a target. You prepare it identically each time, same position, same energy, same environment. Classical expectation would predict it striking the exact same spot in each trial, but that isn't what actually happens. Fire after fire, the electron lands in different locations, apparently without pattern. It's not sloppiness in the setup or a flaw in your measuring instruments. In the quantum world, identical preparations can lead to different outcomes every single time. This unpredictability is not an accident, it's how the physics actually works. This is quantum randomness. It's different from the surface-level randomness in a dice throw where unknown microscopic details, air currents, tiny shifts in angle decide the outcome but in principle could be measured and predicted. Quantum randomness leaves no such hidden trail. Even with perfect knowledge of everything measurable, you can only calculate the probabilities of the possible results. There is no deeper layer of information that would let you choose the winner ahead of time. To describe this, physicists use the idea of a probability wave. Before you measure it, a particle isn't fixed in one outcome or property, it's described by a spread of possible states, each with a defined likelihood. The shape of that spread is determined precisely by the equations of quantum theory, and it evolves predictably over time. But that predictability applies to the probability distribution, not to the specific result you'll get from any single measurement. Once you measure, the range of possibilities reduces to one actual outcome, and the others are excluded from the reality you continue to observe. This is a strange shift in thinking. Macroscopic objects made of vast numbers of particles moving collectively hide these fluctuations. A basketball's molecules average together into a path that looks fixed and predictable, but isolate the behavior of just one quantum object, and the underlying unpredictability steps out from behind the curtain. At this level, the universe behaves like a constant lottery, with new draws occurring everywhere and all the time, even in systems as small as a single atom or photon. The same probabilistic logic governs far more than just a particle's position. Whether a photon reflects or passes through, whether a radioactive nucleus decays now or later, whether a biological molecule changes its structure in one way or another, all of these are events set by probability curves, not rigid scripts. Over time, chains of these quantum events scale upward into the world you experience, influencing outcomes from the microscopic to the very human. Quantum mechanics treats these probabilities as reality's most complete description. Repeat an experiment under identical preparation, and while individual events will vary, the overall statistical pattern will match the theory's predictions exactly. This consistency is why we can design lasers, microprocessors, and medical imaging devices to work with remarkable precision. But the individual quantum events inside remain genuinely random. The fact we can rely on large number averages doesn't change that. Accepting that this unpredictability is built into the fabric of nature opens up thought experiments about what happens if you follow the logic to its extremes. In some interpretations, notably the many worlds view, every possible outcome of a quantum event occurs, each in its own branch of reality. In one branch, the electron hits the detector, in another it misses. Scaled up, in one branch you make it through a dangerous event, in another you don't. The randomness becomes the mechanism that produces a branching structure of possibilities. In your own experience, you get only one chain of events. But if other branches are equally real though inaccessible, then for even the most unlikely survival, there is at least one version of reality where that survival plays out. It's the kernel of the so-called quantum immortality idea. Yet experts such as Max Tegmark have argued that in realistic causes of death, consciousness fades gradually, which complicates the naive thought experiment picture. And philosophers and physicists have raised deeper critiques. In particular, the probability and measure problems that challenge whether subjective survival makes sense in an infinite branching universe. In other words, the leap from quantum randomness to personal immortality is not a physics result. It's an interpretation-dependent philosophical inference with serious points of dispute. The everyday sense of causality, drop a glass and it shatters, emerges from billions of quantum-level events steering toward overwhelmingly probable macroscopic outcomes. In most drops, the atoms making up the glass follow the statistical pathways that produce breakage. On rare occasions, if you could replay the drop countless times, micro-level variations might alter surface stresses just enough to keep the glass intact. In the many worlds framing, both futures exist, each in its own branch. Most branches contain the broken glass, a few don't. That same branching logic is what gets applied, hypothetically, to life and death scenarios in quantum immortality arguments. The essential point remains: at the smallest scales of nature, randomness is not a sign of incomplete knowledge. It is, within our best physical theories, an unshakable rule. And because that rule operates as the statistical engine for all higher-level events, the range of possible outcomes across the whole universe is much wider than classical thinking suggests. Once you see the world in those terms, it becomes natural to ask how such probability landscapes look before a single outcome locks into place, and what it means to talk about an event existing as a spread of possibilities rather than a concrete fact. That's where the picture gets both clearer and stranger when you compare it to everyday experiences, and where the abstract concept of the probability wave starts to feel a little more familiar. Probability waves, Wi-Fi, and bad GPS directions. Think of what happens when your phone's Wi-Fi icon flickers between strong and weak. In that drifting state before it locks onto one signal strength, you have something loosely comparable to a quantum system before measurement. It's a distribution of possibilities, not a single value. Measurement, whether it's your device checking the signal or a detector checking a particle, forces one definite outcome. Unlike Wi-Fi, quantum probabilities are not just epistemic. Quantum theory treats them as intrinsic to how the system behaves. In quantum mechanics, a particle doesn't occupy a single fixed state in the way everyday experience suggests. It might be far more likely to turn up in one location than another, but until a measurement is made, those possibilities all coexist as part of a mathematical wave that evolves according to precise rules. Measurement ends that spread, delivering one clear result in place of many potential ones. The same idea appears in a much cruder form in how an algorithm predicts what you might watch on your social feed. Before you scroll, the platform holds a probabilistic profile of you, a catalog of possibilities weighted by how likely you are to click. As soon as you see a post and either watch or skip it, that cloud of options collapses to a single data point. The analogy works up to a point, but unlike quantum systems, these predictions rest on hidden, knowable causes: your past behavior, content popularity, server timing, that could, in principle, be fully mapped. Quantum physics lacks any comparable hidden ledger to consult. Its unpredictability appears to be built in. A less abstract parallel might be the moment you open a map app in an unfamiliar city. At first, your GPS dot jumps around, sometimes placing you inside a cafe, sometimes in the middle of the street. Until enough satellite signals arrive, the location is effectively a set of plausible positions, shifting and overlapping. When the system finally locks in, the uncertainty disappears with a single decision about where you are. In a quantum setup, the lock-in comes from an interaction, light scattering off an atom, a detector registering a particle, that fixes one outcome from the spread allowed by its wave. It's tempting to think of the blur in these examples as a defect, poor reception, imprecise tracking, but in quantum theory, the blur is not a symptom of bad measurement. It's what the object is prior to being measured, a structure that encodes every possible result of an observation and the probability of each one. The strength of this framework lies in how consistently its predictions match experiment. When particles are left unmeasured, their collective behavior follows the probabilities in their wave exactly. Once they're measured by any interaction large enough to extract a definite value, they behave as if every other possibility has been set aside. This change doesn't require human observers or mental will. It only needs a physical link between the system and its environment that can't be reversed. That's the opening where discussions about many outcomes existing in parallel begin. Mathematically, the wave before measurement is a complete description of every allowed result. Measurement narrows it to one outcome in your account of events, but nothing in the equations demands that the other results be erased from all of reality. For some, that means they remain real in separate branches, inaccessible but still unfolding. You can return to the Wi-Fi picture here. The full set of possible bars exists in the wave before you connect. You only experience one, but that doesn't automatically mean the rest have been annihilated. In everyday technology, we don't imagine the discarded signal strengths carrying on somewhere else. They simply didn't happen. In quantum theory, whether unobserved outcomes persist is one of the deepest interpretational arguments. Seen this way, the probability wave becomes less like a blurry photograph waiting for focus and more like an ordered list of all futures the system can take. Collapse is the point at which your path through that list is fixed, even if other paths remain meaningful in some wider structure. In interpretations like many worlds, collapse is not destruction but branching. Your timeline now follows one track while others carry on without you. This also reframes uncertainty. In most situations you meet day to day, uncertainty reflects missing information, data you could in principle gather to settle the question. In quantum mechanics, uncertainty is part of the object's definition until an interaction forces a decision. Better instruments won't reveal a hidden true state in advance. The most complete view you can have is the evolving wave of possibilities and the probabilities that go with it. Which brings us back to that wayward GPS dot. Its jumpiness before settling is caused by incomplete and noisy data, not by the intrinsic nature of your position. But it makes a useful stand-in for understanding that something, whether a signal, a particle, or a wave function, can be in a state defined by a set of possible outcomes rather than a single one. In the quantum case, those possibilities are not simply placeholders for the result you will discover later. They are an active, physical description of the system until the instant one probability becomes your single observed outcome. The rest is a question of what you think happens to the other options. That last point is where the practical, predictive side of quantum theory parts company from the interpretive side. You can work with the equations to design electronics, chemical reactions, or even experimental tests without deciding whether the unchosen possibilities persist. But once you start asking what really exists before and after a measurement, the conversation turns from calculation to the nature of reality itself. And that is exactly where physicists begin to split into very different camps. Two camps fighting over reality's plot. In professional physics, this disagreement is often framed as a split between two broad attitudes. On one side are the pragmatists, sometimes referred to as the shut up and calculate camp. They treat quantum mechanics as a perfectly honed set of rules for predicting experimental outcomes, without demanding that those rules reveal an underlying picture of reality. On the other are the interpreters, including many worlds proponents such as David Deutsch, Sean Carroll, Max Tegmark, and others, who insist that what the equations seem to say about the structure of reality deserves to be taken seriously, and if possible, explained. The divergence isn't over the math or the data, it's over the weight each side assigns to the question of what's really out there. Pragmatists see the theory as a kind of universal grammar. Master the syntax and you can write consistent predictions every time. Map out the wave function, evolve it with the Schrödinger equation, apply the correct operators, extract the probabilities. If those numbers match observations, and they do with remarkable precision, there's no pressing need to decorate the output with imagery about what happens in hidden layers beneath measurement. To them, the wave function is a calculation tool, no more real than the number 7 is to arithmetic. Interpreters argue that the wave function describes something physical, not just an abstract ledger of possibilities. When the math says a particle's probability distribution includes multiple well-defined peaks, perhaps those peaks correspond to actual outcomes that all occur, each in parallel. In the many worlds view, the branching isn't metaphor, it is the actual evolution of the universal wave function. Measurement doesn't erase possibilities, it locates you in one of them, while the others continue beyond your reach. Every quantum event creates more branches, and all of them are equally real within this framework. These opposing stances persist because so far no experiment has been able to tell them apart. The predictions of many worlds and other interpretations are, with current technology, empirically indistinguishable. That unfalsifiability means the disagreement is as much philosophical as it is scientific. For many working physicists, this is reason enough to leave the question alone. For others, it's precisely why the question remains pressing. Much of the philosophical back and forth boils down to this. Pragmatists focus on predictive power and reliability, arguing that physics isn't obliged to provide a metaphysical story. Interpreters see a missed opportunity in declining to confront what the equations appear to imply. One group finds satisfaction in stopping at the math works, the other sees that as only half an answer. The popularity of many worlds among some interpreters comes from its elegance. The equations operate without modification and no special collapse rule is needed. You get branching simply by following the math, solving the Schrödinger equation for the whole universe. From here, speculative ideas like quantum immortality emerge. If branching is real, then in every situation with a non-zero chance of survival, there exists at least one branch where you live on. Your subjective experience could, in principle, follow that unbroken survival thread indefinitely, however improbable it looks from an outside perspective. Pragmatists push back hard against that leap. Accepting many worlds as the literal truth is one thing, layering on a personal survival guarantee is quite another. The equations do not privilege one branch over another, nor is there evidence that consciousness chooses the survival path. From a single world standpoint, the outcome of a life-threatening event is whatever happens in the one reality we share, determined by chance but final in its consequences. Between these poles sit a range of intermediate positions. Some physicists hold that the wave function is real but does collapse under certain conditions, which trims away the extra branches without abandoning physicality. Others speculate about undiscovered rules that might reconcile the apparent randomness with a hidden order. Still others borrow elements from many worlds without accepting it wholesale. Regardless of stance, everyone uses the same formalism to do the actual work, designing experiments, operating quantum devices, and testing predictions. That shared toolbox is part of why the disagreement hasn't stalled progress. Quantum mechanics powers technologies from lasers to superconducting circuits to quantum computers, all of which rely on the math, not on winning the interpretation war. In the lab, calculations matter more than metaphysics. In thought experiments, however, interpretations like many worlds can radically change how you imagine your own trajectory through the universe. Personal perspective plays a big role here. If you adopt a single worldview, improbable survivals are just luck, and luck eventually fails. In the many worlds narrative, somewhere in the branching wave function is a continuous chain of versions of you that keep going, no matter how many close calls occur in other branches. The same equations support both views. The difference lies entirely in how you think about the outputs. The split runs deep enough to have persisted for decades, and the lack of decisive experimental leverage keeps it in place. A definitive test, one that could clearly distinguish a single persistent world from an ever-splitting wave function, would be a turning point. Until such a test exists, the debate stays open, with pragmatic restraint on one side and interpretive boldness on the other. If you assume the literal branching picture, then right now there are versions of events in which every allowed outcome is playing out. Among them is a narrow run where every hazard misses you purely by chance, and that run is the only one you would ever be aware of from the inside. Whether that strikes you as a comforting loophole or a hollow abstraction depends on which account you accept. And before weighing that reaction, it helps to understand exactly what the many worlds idea does and does not claim, especially compared to the popular images it often gets mixed up with. The quantum crossroads, one world or infinite branches. At this crossroads in quantum theory, the many worlds interpretation offers a radically simple answer. The universal wave function is not just a calculation tool, it is physically real, and branching is an unavoidable consequence of its smooth, unitary evolution without collapse. In this account, quantum mechanics never chooses a single outcome. Instead, every possible result allowed by the wave exists, each in its own branch, and all branches together make up reality. When most people hear many worlds, though they tend to imagine the tropes of science fiction, parallel Earths with wildly different histories, or neat timelines that can be crossed if you find the right machine, that picture misleads. In modern physics, many worlds describes an unbroken, continuous process occurring at the smallest scales. Every time a quantum event unfolds, any situation where the probability wave allows more than one result, the structure of reality incorporates all those results. There's no dramatic fracture, just steady, microscopic accumulation of differences as branches form. Quantum event can be as unremarkable as an electron taking one path instead of another in a microchip, or an atom releasing a photon now rather than a nanosecond later. Before any measurement, such alternatives coexist in the wave function. Afterward, in the many worlds view, each is real in its own branch. These branches are not separate universes floating side by side in space. They are distinct components of the single universal wave function, which evolves without discarding any terms. The branching is constant, happening in countless systems around you at every moment. In everyday terms, branching unfolds quietly, even when you seem perfectly still. The molecules in your body are constantly involved in quantum processes with multiple possible outcomes. Every one of these outcomes plays out in some branch. The sheer pace and number of these events make the branching structure unimaginably vast. Attempting to list even the splits of the last second would be hopeless. From your own perspective, though, you never sense this multiplication. You experience a single, continuous history, the sequence of events corresponding to just one path through the branching web. Suppose a quantum coin could land on heads or tails with equal probability. In this interpretation, both happen one in each branch. In the heads branch, a version of you saw heads. In the tails branch, a version saw tails. After the split, their futures diverge independently. Why don't these versions interact or exchange information? This is where decoherence enters. Decoherence is the process by which different outcomes, though part of the same overall wave function, rapidly lose the ability to interfere with each other because of their entanglement with countless environmental degrees of freedom. Once that entanglement happens, the branches are effectively sealed off. Each continues to evolve according to the same laws, but the correlations that tied them together fade beyond retrieval. Decoherence explains why the branching appears clean and why you feel locked into one branch. However, as research points out, it doesn't by itself solve the deeper measure and probability questions. Physicists like David Deutsch and David Wallace have developed decision-theoretic approaches to explain how the standard quantum probabilities might emerge within many worlds. Others, like Lev Vaidman, have critiqued these ideas or offered alternatives. The mechanisms are under active debate even among proponents. Understanding this split between mechanism and interpretation is easier if we separate the ideas. Branching means that all possible outcomes of a quantum process remain in the universal wave function. Decoherence explains why those outcomes stop interfering and act like separate worlds. Your perception of a single, unbranching reality is simply the subjective view from inside one decohered branch. This interpretation also reframes familiar cause and effect. Each moment in your life sits on the surface of a vast tree of branching possibilities. Walk through a doorway and photons scatter into your eyes in one particular way in your branch, but in another, slightly different scattering pattern in another branch. The differences are often microscopic and unnoticed, but they stack over time. Eventually, they add up to visibly different events. Conversations taking new turns, decisions coming out differently, hazards avoided or encountered. If you want a mental model, picture a river that endlessly channels into smaller streams which themselves divide again and again. In many worlds, there is no pause in the splitting and no smallest possible branch to stop at. Your current sequence of moments is one channel of that river. Nearby are other channels that shared your past up to some tiny event but now flow elsewhere. Applied to human survival, the logic has a peculiar consequence. If some event has two possible results, survival or death, then in this framework both happen. Some branches end the line of moments that contains you, but in others, the surviving version continues. Across a series of such events, there will always exist at least one chain of branches in which you survive each time. Inside that chain, the experience is one of uninterrupted continuity. Outside it, the overwhelming majority of branches end differently. Importantly, many worlds doesn't single you out. Branching is not about observers, it applies to every physical system. You, your body, and your consciousness follow the same rules as any other collection of particles. The version of you in one branch will never recombine with the version in another. Even if they remain nearly identical in the moments after split, different quantum events will quickly nudge them onto paths that diverge further and further. Rather than a tidy set of parallel universes with defined edges, the picture is one of a single, ever-expanding, intricately connected wave function. Every branch contains its own self-consistent history, all running forward under identical physics. The you in each branch exists only within that branch's chain of moments, while other branches carry different sequences you will never encounter. None of these branches is privileged, all are part of the overall physical state. Grasping this model gives context for why the quantum immortality idea exists at all, and why it is controversial. It emerges not from fantasies of world hopping, but from the internal logic of applying many worlds to situations with life and death stakes. And while decoherence makes the branches behave like separate worlds, deep questions remain about how to weigh or interpret them when it comes to probabilities or subjective experience. The next step is to bring this down from the grand, cosmic scale to something more concrete. Instead of imagining improbable survival as an abstract path through a theoretical branching structure, consider how the same logic might play out in a setup you could literally power on with equipment that already exists. Once the scale changes, the mechanics stay the same, but the experience becomes far more personal. Immortality by statistical elimination. Consider a purely hypothetical setup, designed only as a thought experiment. On your desk is a small, sealed quantum circuit connected to a device with two possible outcomes, a green light for safe and a red light for danger. Each outcome would represent the difference between continuing as before or meeting a severe, irreversible endpoint without any actual harm taking place in reality. This is purely imaginary, a stand-in for understanding the idea without crossing ethical boundaries. Physicists and ethicists alike warn that such experiments are hypothetical and morally impermissible. They are tools for thought, not action. In fact, leading researchers such as Anthony Aguirre have explicitly stressed that quantum suicide scenarios must never be attempted in practice. In this imagined setup, the device is programmed so that the color it shows each time is determined directly by a quantum event, something inherently unpredictable even with complete knowledge of the system. No concealed algorithm or hidden mechanical randomness is involved. The result comes from the indeterminacy built into quantum physics itself. When you play, you activate the circuit, it enters a delicate state, and a fraction of a second later reality picks one path, green light or red. In our safe mental model, a red light would simply signify you're out in the rules of the thought experiment, without any actual injury. Under the standard single-world picture, every press of the start button has a set probability of yielding green, and a complementary probability of yielding red. If you play enough times, those odds multiply out to make uninterrupted survival through many rounds astronomically unlikely. In a familiar probabilistic sense, small losses accumulate until one ends the sequence. In the many worlds description, things unfold differently. The quantum event doesn't eliminate one possible result, it realizes both. In one branch of reality, the device shows red, and by the rules of the thought experiment, your participation ends there. In another branch, it shows green, and you continue to the next round. These branches are completely separate. Nothing from the red path bleeds into the green, and vice versa. But in your own experience, you inhabit only the branch in which you see green. The timelines where you didn't are inaccessible. Repeat this enough times and the branching becomes immense. On the grand scale, most branches terminate quickly, consistent with the single-world expectation. Yet there will always be at least one branch where the green outcome appears every time. In that branch, you pass every round, no matter how improbable. It exists because quantum mechanics permits it, and in many worlds, anything permitted happens somewhere in the wave function. From inside that uninterrupted survival path, you feel nothing unusual. There's no signal that you are in the rarest possible sequence of events. The improbabilities don't accumulate in a way you can sense, they simply never happen to you. What would feel like extraordinary luck from the outside reads as ordinary continuity from within. You've never personally experienced the red outcome, so your memory contains only a streak of greens, as if that were the norm. This framing is what gives quantum immortality its provocative appeal. If many worlds is a correct account of physical reality, there is always a branch in which you make it through the next event alive. The exact probability doesn't matter as long as it is non-zero. Following only the safe branches, in principle, you never encounter your own death. Mathematically, it means your path always lands on the surviving side of the outcome split, however absurdly unlikely that seems in the larger picture. Replace the harmless lab device with the unplanned hazards of ordinary life, and the logic holds. The world is full of small uncertainties, slight shifts in timing, molecular interactions, environmental fluctuations where outcomes differ microscopically each time. Most of these changes are inconsequential, some aren't. Occasionally, the spread of possible results includes one that stops your story entirely. In the branching view, there is always some fraction of branches where that doesn't happen. The result in such a model is not a life free from danger or harm, but one in which fatal outcomes never land in your own sequence. You could still be injured, still suffer, still take risks and lose, but never in a way that fully ends your conscious perspective. A run of close calls, recoveries against the odds, or unlikely escapes might pepper your life, but to you that would feel like the natural way events have always unfolded. After all, you would have no memory of the branches where they didn't. From the outside, in the space of the universal wave function, this continuation is unspectacular. Your endless chain of safe results is just one of countless patterns, and most others do not resemble it at all. Nothing in the physics gives that chain preference, it draws significance only from being the path you occupy. From the interior view, the rest of the structure is inaccessible, so the singularity of your streak is invisible. It's here that the thought experiment shifts in tone. The survival branch might block endpoints, but it includes every other kind of outcome. That means it can contain prolonged illness, accidents that maim but don't kill, losses with no recovery, anything short of complete cessation. The principle, if real, is stark: continuity without any guarantee of quality. To imagine it as a universal safety net is to misunderstand its scope. It's not protection from harm, only from annihilation. Even stripped to a safe, binary device on a desk, the mechanism in this hypothetical is the same principle behind the more dangerous images people attach to quantum suicide. In a collapse-based view, improbably long streaks happen only rarely and end naturally. In a branching view, such a streak must exist somewhere, and if you are in it, every elimination event filters out the branches where you were. The apparent miracle is just the flip side of ordinary probability. Your experience is restricted to the survivor path because all others, by definition, contain no more of you. This reversal of statistical expectation is the core of immortality by statistical elimination. In normal probability, non-zero risks compound to produce near certainty of eventual loss. In the many worlds framing, even the smallest survival chance produces a path where loss never occurs, and for the observer inside it, that path is the only reality experienced. The unsettling part lies in picturing what it would be like to remain on that path for as long as quantum events unfold, watching other stories end while yours carries on unbroken, with no moment when you can observe how rare your situation really is. Understanding this logical inversion sets up an important context. It invites questions about how you might usefully explore such branching in safe, controlled, and entirely hypothetical ways, and what technologies could model it without crossing any ethical lines. Recent breakthroughs that make this less science fiction. In early 2025, the headlines in quantum research were full of results that even a few years earlier would have seemed out of reach. Laboratories working with trapped ions and photonic links reported high-fidelity teleportation of qubits over distances far beyond a single experimental table, reaching scales that connected entire facilities. In practical terms, researchers could now create entangled particles, separate them by many kilometers, and maintain their shared quantum state long enough to perform operations with accuracy levels that avoided the need for constant redundant checks. Fidelity numbers, how precisely the transmitted quantum state matched the original past thresholds that had only appeared in theory, with error margins so small they could be relied upon without excessive repetition. Entanglement itself has been a known phenomenon for decades, but preserving it over these distances without its delicate correlations collapsing to environmental noise has always been the bottleneck. Improvements here weren't the product of a single breakthrough, but of incremental gains in isolation, shielding, and control, better vacuum systems, more stable cryogenic enclosures, and laser pulse sequences tuned to minimize disturbance. Each refinement shaves away at decoherence, allowing those fragile quantum relationships to persist for far longer than before. At the same time, new fabrication techniques are transforming the qubits themselves. For example, in 2025, NIST SQMS reported major qubit fabrication and coherence improvements, using advanced encapsulation and precision nanofabrication to dramatically extend the lifetime of superconducting qubits. Other arms of the field pushed on very different frontiers. In 2024-2025, TU Dortmund demonstrated a time crystal system persisting for more than 40 minutes, an astronomical leap over previous lifetimes. And a Science Advances paper described Bell inequality type violations using indistinguishable photons, tightening the experimental grip on questions of non-local correlation. These kinds of results expand the range of quantum behavior scientists can test directly, but they don't prove or disprove specific interpretations like many worlds or the idea of subjective immortality. What they do is give researchers a much broader and more precise toolkit for observing, manipulating, and linking quantum events in the real world, so that experiments can be designed to probe the dynamics underlying those interpretations more closely than before. One application of these refinements has been in quantum teleportation experiments, where the state of a particle is destroyed at its origin and reconstructed at a distant site using both classical information and an entangled partner as a carrier. Reliable long-distance teleportation depends entirely on sustaining high-quality entanglement, because any corruption in the correlation between the two particles will degrade the transferred state. Extending teleportation over kilometers without performance collapse allows quantum events in one location to influence linked outcomes in another, still bounded by quantum unpredictability but now separated in space without loss of coherence. While this isn't the cinematic version of beaming objects, it is the dependable transfer of quantum information, an essential component for future distributed quantum systems. In parallel, the performance of quantum computing hardware has been accelerating. Early generation machines suffered from such high error rates and slow gate speeds that deep computations were pointless. The system would decohere long before completing a useful sequence. By 2025, industry and academic platforms alike were reporting both significantly higher gate speeds and sharply reduced error probabilities. Faster gates mean an algorithm can be executed in less time, avoiding some decoherence losses, while lower errors mean fewer corrective cycles, freeing qubits to focus on computation instead of constant state repair. Although the media often focus on headline applications like breaking encryption or modeling complex materials, these hardware advances have another less flashy purpose, making it practical to simulate quantum systems in detail. A chain of entangled measurements is mathematically a multi-branch structure, and simulating it demands resources that grow beyond classical computing very quickly. Stable, fast qubits allow researchers to evolve these branching probability landscapes over time, tracking how different possible outcomes appear, change, or vanish as the quantum system interacts internally and with its environment. Such simulations can't settle whether those branches represent literal parallel worlds, but they can make the connection between theory and behavior far easier to grasp. Instead of an abstract probability table, you can watch a simulated state change shape as events multiply the possible outcomes. Gains in stability mean these virtual branching trees can be extended deeper without drifting into meaningless averages from accumulated errors. For many researchers and students, this shift turns diagrams in a textbook into something closer to a working model you can interrogate step by step. High-fidelity links add a physical dimension to these models. By tying parts of a simulation to real qubits in distant labs, each part measured and fed back into the system, you can create demonstrations that show linked quantum outcomes arising in separate places in real time. This reinforces the point that quantum randomness is not constrained to one location. The constraints are imposed by decoherence and measurement, not by distance. With these tools, researchers can stage controlled, statistically extreme scenarios in a way that was only theoretical before. Linking a sequence of entangled decisions and watching how long a single improbable path survives before reverting to the expected distribution can now be done without pushing the hardware beyond its limits. The data from such runs not only illuminate how correlations degrade over time, but can also test how robust linked outcomes are when stressed by environmental noise or rapid repetition. The fact that such chains can be maintained by current machines marks a shift toward practical exploration of quantum probability structures, even if the setups are many orders of magnitude removed from the life and death frames of thought experiments. The important point is whether these demonstrations reveal evidence for or against any particular interpretation. It's that 2025-era technology can now sustain and manipulate quantum states with enough control to make those interpretations more than abstract debates. Models can run longer, experiments can link more components over greater distances, and measurements can be taken with fewer compromises. In effect, experimental reach is catching up to the kinds of scenarios that, until recently, could only be described verbally. For the wider audience, the takeaway is subtle but significant. Elements that once seemed like set dressing for speculation now appear as live, measurable phenomena. Entanglement over long distances, precise gate operations, extended coherence times, and simulations that map the full range of possible outcomes over many connected events are not hypotheticals. They operate in labs today. The improbable outcomes central to certain interpretations sit alongside the likely ones within these models, and both can be assigned measurable probabilities that shift predictably as the systems evolve. None of this confirms that someone could, in any personal sense, follow an endless thread of survival through branching events. What it does is strip away some of the former distance between abstract theory and what can be physically arranged, observed, and calculated. Linked randomness, persistent correlations, and branching style structures can be seen in action, under conditions choreographed by the experimenters. It changes the conversation from "this is what the math suggests could happen" to "this is a functioning quantum system whose measured parameters match the same equations." By closing that gap, the new tools also raise another issue, one that no improvement in coherence time or gate speed can settle. After all, showing that a quantum system will produce every allowed outcome still leaves open a human-specific question. When the branching happens, what fixes which outcome you personally experience? Consciousness, the missing variable. In the middle of the wider conversation about branching universes, another question keeps pressing for attention. Could consciousness itself be part of the machinery? Quantum mechanics, as it is normally written, says nothing about minds. The equations describe systems, measurements, and outcomes in entirely physical terms, and in those terms branching happens whether anyone is there to witness it or not. Still, to anyone actually having an experience, reality always comes as the one you are aware of. Whether that connection is only coincidental or points to a deeper link remains unsettled. The straightforward position treats the mind as a classical system. Neurons fire, chemicals diffuse, and electrical impulses travel along axons. Thoughts, memories, and decisions emerge from networks of physical interactions that, however complex, behave like other large-scale processes. In this view, your brain is no more relevant to quantum physics than your pancreas or your skin. Consciousness is an emergent effect of parts interacting, not the product of delicate quantum states, and the branching of events after a quantum process has nothing to do with what your brain happens to be doing. Some researchers, however, have argued there may be room to question that separation. Since the 1990s, and with more activity again in 2024-2025, cross-disciplinary teams have begun probing whether certain brain processes might involve quantum effects in ways classical models miss. Notably, recent experimental work by Joseph Wiest at Wellesley reported that microtubule binding drugs can alter anesthetic response in rodents, a finding that intersects with older theories linking microtubule dynamics to cognition. Exploratory collaborations, such as projects at the Allen Institute, are also mapping neural and molecular structures with an eye toward whether quantum-sensitive interactions could have functional roles. These projects are still far from presenting proof, but they have prompted renewed, careful discussion about whether trace quantum behavior in the brain is possible. Mainstream neuroscience remains cautious. Figures like Christoph Koch at the Allen Institute and physicists such as Max Tegmark have pointed out that the brain's warm, wet, noisy environment is exactly the kind of setting where quantum coherence should evaporate almost instantly, drowned in thermal noise. Tegmark's calculations suggest any coherent quantum state in neural tissue would decohere in times far shorter than a neuron's signaling window, making it unlikely to directly influence thought. The prevailing consensus is that ideas about quantum processes as the source of consciousness are speculative and not supported by the bulk of available evidence, even if small-scale effects aren't yet completely ruled out. Some of the renewed interest comes from scale and timing. Neuronal substructures, microtubules, ion channels, vesicle release sites operate in regimes not wholly removed from where quantum effects can set statistical biases. If in principle some quantum-level change could nudge the timing of a neuron's firing, and if patterns of such firings underlie conscious moments, then the mental narrative and the unfolding of physical events might be less independent than assumed. So far, though, this remains an if-laden scenario without direct measurement to support it. That's why early claims linking consciousness to branching have been treated warily. To actively influence which branch continues as your experience, a mental state would need to participate in something like the collapse or effective collapse of a probability wave. That task demands a precise definition of measurement and a coherent physical account of awareness, neither of which is within reach. Without predictions that cleanly separate a consciousness selects branches process from ordinary decoherence, these remain intriguing thought experiments rather than viable laboratory tests. Still, there's an everyday pull to the idea. Subjective awareness feels like a single, continuous thread, not a blur of equally real alternatives running in parallel. When you wake, you pick up where the day before left off. You don't perceive yourself as spanning many almost identical mornings. That stubborn continuity gives the impression of selection, whether or not the physics grants you any steering role. One way to frame it is through a vignette. Imagine your awareness as a stubborn app on a phone, something that simply refuses to close. Try to swipe it away, shut down the phone, or drain the battery, and when the system restarts, the app is still there in the foreground. In a branching context, each offloaded tab or clone process would be like a version of you in a different branch, running somewhere unseen. But the one in front of you now is the only one you directly inhabit. If the app never closes in this branch, continuity persists. In the strong version of the theory, this persistence is what quantum immortality relies on. Wherever the branching produces multiple possibilities, you only ever occupy those in which your awareness is still active. Outcomes without you are, by definition, inaccessible. They fade from your personal record not because you left them, but because there is no you there to observe their unfolding. In versions that give consciousness an active role, your presence wouldn't just be surviving. Your being here would help define which branch counts as survival in the first place. The stakes, if that were right, would be enormous. It would suggest that the reason you remain alive through improbable strings of events could be a property of awareness itself. But even the scientists most closely involved in quantum theory emphasize the gap between such speculation and evidence. The current experimental probes, whether measuring microtubule responses in animals or mapping neural dynamics with quantum-tuned sensors, are exploratory, not proof. For now, the more defensible statement is that nothing in standard quantum mechanics requires consciousness to influence branching, and nothing in mainstream neuroscience shows that it does. The possibility remains open enough to keep interdisciplinary discussions alive, but the balance of opinion holds that cognitive processes are classical unless shown otherwise. Explorations by groups such as those at Wellesley and the Allen Institute may uncover interesting biology, but whether any such findings would rewrite our understanding of consciousness is anyone's guess. That lingering uncertainty is part of why the question keeps resurfacing, because if any link between awareness and branching were confirmed, it would ask us to rethink both the physics of the micro-world and our place in it. Even without proof, the conversation reframes survival in the branching universe picture, not purely as a statistical fluke, but possibly as something with a mental dimension. In that light, the puzzle isn't just about how matter behaves. It's also about how minds, whatever their physical basis, inhabit sequences of events and stitch them into a personal history. Whether the stitching is passive, active, or illusory shapes how we think about identity in a reality that may never settle on just one outcome. And from that question, it's a short step to wondering how these patterns might emerge in systems far removed from biology, places where minds are not born of neurons, but of code. Immortality in an age of AI and digital selves. Artificial intelligence now creates vast numbers of plausible personas with almost no effort. A single system can generate hundreds of unique characters, each with its own background, habits, and ways of deciding that behave as if they were distinct individuals. In a branching universe analogy, they're like alternate versions of an origin point, instances with the same starting conditions that then diverge as soon as they begin interacting with their simulated worlds. Some of these digital lives might run for long spans of simulated time, others disappear after moments. None need to believe they are the original for their worlds to keep functioning. This is ordinary work for modern AI architectures. Starting with the same prompt, a cautious scientist orbiting a distant planet, large language models can produce countless variations. Slight differences in internal randomness or small changes in context send each run along its own trajectory. These are not physical branches in the quantum mechanical sense, but the logic is parallel. A single starting point gives rise to multiple possible continuations, and the one you inhabit as a user is just one thread among them. The rest exist as saved states, logs, or discarded outputs, other branches you could have seen in different circumstances. You already interact with smaller-scale examples. Your digital life is scattered across email inboxes, archive chats, photo libraries, forum posts, playlists, and old save files. Each of these captures a different slice of your preferences, abilities, and self-presentation, sometimes separated by years. Your posts from a decade ago still exist next to your current ones. Long-abandoned avatars remain in game databases. If someone browses through them, they find many moments that could have been starting points for alternate versions of you that never actually developed. Some versions keep running without you. Forgotten playlists continue to generate algorithmic recommendations. Social media accounts you don't visit still receive engagement or surface in search results. An old cloud album reappears in a memories notification. If you picture yourself as a moving point along one timeline, your digital presence has already fractured into countless points stored in parallel, each one preserving the state of you, as you were at its creation and carrying traces forward in its own way. This makes it easier to imagine a branch that exists entirely in code. An AI system trained on your writing style, preferences, and personal history can produce a model that behaves recognizably like you. As it interacts, whether with a simulated world or live inputs from the internet, it accumulates memories and choices that gradually push it away from the original source. The chain of moments it generates becomes a distinct history, much like diverging branches in a physical universe metaphor. Here, the analogy tempts overreach, so it's important to draw a clear line. Digital backups in AI instances can persist and diverge, but that persistence is an engineered form of redundancy, not subjective continuity. Copies can exist and develop in parallel, but the conscious perspective you inhabit is not transferred simply because a program reproduces your outward behavior. Whatever continuity you experience moment to moment is unique to your biological system unless proven otherwise, no matter how convincing a simulation might be. For now, most researchers agree that AI does not have awareness. Current systems lack the continuous self-modeling and physical embeddedness of human minds. They can be designed with memory, adapt goals over time, and process multimodal information streams, but this yields convincingly varied behavior, not proof of inner experience. The discussion persists because each new generation of systems gains more of the components that, in theory, would be required for more lifelike simulation. Seen from the branching perspective, each run of a simulation is analogous to collapsing a probability wave in quantum mechanics. Before you press go, the system can be thought of as holding all the possible ways the interaction could unfold. Once you run it, you witness one path. Run it again from the same starting parameters and you get another, branching off in a different direction. In physical reality, the other branches can't be rewound, paused, or deleted. In code, they can. But in either case, each path looks linear from the inside, even if it's one of many from the outside. This also changes what immortality means when you move the concept from biology to software. A digital facsimile of you built to match your manner of speaking, deciding, and recalling could continue generating new moments after you stopped. In that environment, the idea of survival simply means that at least one instance remains active. With redundant copies and backups across servers, it's easy to ensure that somewhere one version carries on, even if others are switched off. In quantum immortality, the physics preserves at least one survival branch. In software, redundancy preserves at least one running copy. Neither case requires supernatural intervention, only mechanisms that allow multiple possible continuations with at least one being sustained. The distinction is that in software, an external observer can switch between versions at will, duplicate them, or inspect their full histories. In human experience, a conscious path has no such access to alternates. It is locked to its own unfolding. This is why the analogy works structurally without pretending the phenomena are identical. Both involve trees of possible sequences where one line remains uninterrupted, but only in the AI case can that survival be managed deliberately. From an engineering standpoint, keep at least one branch alive is a mundane requirement. Redundant arrays, geo-distributed backups, and fault-tolerant load balancing are industry standards. Yet structurally, this is the same minimalist definition of immortality used in the many worlds thought experiment. Within the full set of possible paths, one never terminates. In AI, that continuation is a design goal. In human life, it would, if the interpretation is correct, be an unchosen consequence of how reality operates at its most fundamental level. Looking at your existing online presence through this lens makes the layering even clearer. Every profile, archive, and saved file is the equivalent of a paused or dormant branch. Re-engage with one, log back into an old game, resume an abandoned blog, and it will now diverge from where you are today. Your identity, in practical terms, already exists in many parallel developments in digital space, even before you factor in whatever physics may be doing beneath it all. This reframing doesn't collapse the boundary between digital branches and biological ones, but it does soften it. Both are systems capable of producing and sustaining multiple different lines of development from the same starting state. In one case, the substrate is physical reality itself. In the other, it's a network of processors and storage media. The structural parallel is what makes the AI analogy compelling, not an assumed equivalence of consciousness. So the persistence of a software instance can certainly mirror the survival branch in a thought experiment. But for us, the question is more personal. Our only confirmed perspective comes from within a single, irreplaceable biological stream of moments. In that sense, your AI double can keep going forever in code without that endurance transferring to you in any meaningful way. Recognizing this difference adds caution to the temptation of thinking about immortality as simply keeping something that looks like me running. What persists in code is an asset you can watch, pause, and edit. What persists in you is a thread you inhabit without outside access. Bridging those is not just a matter of better data or faster hardware. It would require solving the open problem of subjective continuity itself. And that leads to a broader, unsettling question about where we place the meaning of survival. If a system staying active is enough to count, even when awareness isn't part of the picture, the concept of immortality could be applied to any redundant process. But if survival means preserving a conscious vantage point, then the branching logic that makes digital endurance trivial remains an unanswered puzzle for us. If survival can mean a persistent software instance, what does you really mean? Why you probably shouldn't test this yourself. In discussions about branching histories, it's easy to be drawn to the version where things turn out in your favor. In the quantum immortality framing, that's the survival branch, the one in which you keep going. But that single thread is surrounded by countless others where events end very differently. For every path where you avoid harm, there are many more where you don't. If the many worlds picture turns out to be correct, those other versions aren't abstractions. They are as physically real as the one you are aware of now. Your continuation doesn't erase them, and they carry on in their own trajectories with all the consequences you evaded here. That reality is the part often glossed over when people imagine themselves as endlessly lucky. You don't get to gather experiences from across the different branches. You only inhabit one, and in the branches where you didn't make it, there's no awareness left to notice. If an impossible outside view of the whole structure were available, your run of good outcomes would appear as one thin strand winding through a vast web of endings. The rest would remain sealed off, unreachable, still unfolding without you. This is why the thought experiment should remain exactly that, a mental model, not a blueprint for action. Even the most generous speculative reading of many worlds offers no method for moving between branches at will. It does not give you control over which outcome you witness, and it certainly does not permit you to engineer high-risk scenarios in the belief that some version of you will always be safe. That way of thinking may sound appealing in the abstract, but from within your one confirmed experience, there is no assurance you'll be in the branch where survival occurs. From the standpoint of established physics, the existence of branching universes remains unproven. Many worlds attract supporters because it keeps every solution to the wave function and removes the need for a special collapse rule. But other interpretations match the data just as well, and none has been verified as the final answer. Treating many worlds as a settled fact means wagering your only verified life on a theory that is still under debate. This is also the ethical red line. Leading voices in the field, including cosmologist Anthony Aguirre, have explicitly warned that taking a quantum thought experiment and turning it into a real-world, life-threatening test would be both unethical and scientifically misguided. Risking irreversible harm to see what happens is not an experiment, it's self-destruction. No genuine research program in physics would ever sanction such a trial. In classical probability, dangerous events accumulate the longer you expose yourself to them. Testing quantum immortality by taking deliberate physical risks doesn't reveal which interpretation of quantum theory is correct. It just raises the chance that in the branch you experience, the outcome will be fatal. If the universe works according to collapse-based interpretations, there is no parallel outcome to slip into. The wrong result arrives, and your story in this one, the only one you can ever confirm, ends. A helpful image is a game that deletes your only save when you lose. You could convince yourself there's an invisible backup somewhere ready to restore your progress. In a digital environment, maybe that gamble is worth the curiosity. In real life, if such a backup doesn't exist or exists in a form you can never load from here, your only run is gone the instant the bet fails. Destroying something irreplaceable because of a speculative belief in a duplicate is the same kind of gamble. You could erase the only draft of an important project or obliterate your entire photo archive under the assumption a flawless copy exists, only to discover too late that it doesn't. There is no undo in the version of events you inhabit. The appeal of quantum immortality rests on the all branches perspective, a view no observer inside the system can access. From the inside, the only probabilities that matter are the standard ones. If they break against you, there is no perceptible safety net. Believing in one doesn't make it present in your current frame of events. Each branch is isolated. There is no path back to outcomes where you survived. So there's a more grounded application of the idea. Maximize the proportion of possible branches you'd want to be in. That means avoiding stacking your present with unnecessary high-risk events. Choices that reduce easily preventable harms leave more branches that fit your own definition of a tolerable or flourishing life. Think of it as curating the subset of futures most worth experiencing. Of course, you can't control all the contributing factors. Quantum-level randomness still works its way into every larger system, whether you invite it or not. But just as skill and strategy can tilt odds in a competitive game, caution and good conditions can tilt the odds toward branches with good outcomes. While you can't dictate which branch you'll awaken in tomorrow, you can influence the conditions that shape the set of branches available. This also reframes the objective. In the most extreme reading of quantum immortality, as long as there's any survival probability, continuance happens somewhere. But there's no implied guarantee of well-being in that continuance. A branch could preserve life in forms you would find intolerable just as easily as it could preserve the comfortable, healthy version of you. By trimming the obvious hazards, you bias the set toward outcomes worth living through, rather than just avoiding annihilation. Seen that way, quantum immortality, if it were true, would still be an argument for risk management, not for recklessness. It's not a backdoor into invulnerability. It's a reminder to care for the trajectory playing out in the only branch you can influence from here. To protect what matters, you'd safeguard your current timeline like you would your only copy of a critical file, backing it up where possible, but never destroying it on the hope the backup is actually there. Even if future experiments someday weigh in on whether many worlds is correct, this basic principle remains valid. In every scientifically credible picture of reality, your present awareness is real, and destructive decisions can end it. Theoretical infinities of other possibilities, whether existing or not, have no role in undoing a mistake in progress. The only resilience you can prove having is the kind you create by maintaining the conditions you already inhabit. That's the branch that is still moving forward and can still be shaped. In other branches, other versions may already have ended their run. The only one in front of you is this one, and it's here that your decisions still operate. If you want to explore these ideas, read the thought experiments in the philosophical critiques. Don't try to perform them. The concepts remain most useful as tools for thinking about probability, perspective, and the structure of reality, not as invitations to gamble with the one life verified from your own point of view. And with that perspective in place, we can turn to a final consideration. How whether or not many worlds is true, our current tools already let us examine probability and branching more closely than ever before, and what that means for the life you are living right now. Whether many worlds reflects reality or not, current quantum tools let us examine branching-style dynamics with unprecedented clarity. We can model them, measure them, and watch their probabilities shift, but there is still no proof that observers can be immortal within these systems. Your best practical move is to shape the branch you actually occupy, not to gamble on theoretical escape routes. That's where your decisions have real influence and real consequence. If this left you with more questions than answers, good. Share the thought experiment that stayed with you most, and subscribe if you want more deep dives like this.